Yeah. Okay. Hello, everyone. Today we have Issac Wang from Fermilab telling us about imprints from light dark matter on evolution of cosmic neutrinos. Take it away, Issac.
Okay. Thanks for the invitation. I think this is my first time.
You notice that in your slide is collaboration, right?
Yeah.
It's
Collaboration. Oh, yeah. That's still be typo here.
Carlos said our in-house is
This is funny, collaboration.
You know, the first talk I gave in front of Carlos, he picked up like one word I spelled wrong. It was phenomenology. I spelled phenomenology wrong.
Oh.
I
Still higher him.
You can try to spell the longer name like it's phenomenologist and try to see whether it's a higher probability to make it wrong.
Yeah, the amount of syllable. Okay, sorry.
This is a very recent work from me and one of my collaborators in China, who is a young assistant professor in Institute of Hydrogen Physics. I think maybe he joined there in 2021. And this is a work that was finished on exactly the last day of the last year, or the last 2 days in the last year. I don't remember. Yeah, but that was the case. So we were talking about how light dark matters, if they interact with the standard model neutrinos in the universe, and how they can produce, and what kind of cosmological inference can they left to be observed right now. Is it working?
Maybe click the arrow once and then.
Okay.
Yeah.
Okay, a quick view. I will show all the results later in detail, but this is just a quick review. This is a brief thermal history of the light dark matter created from the neutrino pairs in the standard models. We're going to consider the simple and basic general framework from standard model neutrino pairs goes to dark matter pairs, and they're produced mostly after the neutrino decoupling. And they can be both free in dark matter or freeze out dark matter, which means they can be either in thermal equilibrium with the thermal mass or not. And the most important cosmological imprints that we're expecting is the C-nu-B distortion. You can see that the standard C-nu-B distortion is basically this curve, but we expect some things can happen here so that the energy tail could be raised.
C-nu-B is the cosmic neutrino background.
Cosmic neutrino background.
We haven't seen that yet.
I see some people use this notation.
No. I mean, have we observed cosmic neutrino background?
Not yet.
Not yet.
But you will tell us that we can.
Yeah. Some experiments claim that they can, like Ptolemy.
Yeah.
Well, they
That is controversial.
Yeah.
But continue.
They say they can. If they say, then let's encourage them to do it, right? Okay, all what I'm going to talk about today, standard model of dark matter. What is the dark matter from neutrinos? That's could be a very brief introduction because I believe everyone here should be very familiar with dark matters. And Boltzmann equations, which is of course, the key equation to govern everything of the thermal history of the dark matter. And following is the three options that we considered as the cosmological imprint that we are going to observe. So the first thing is the introduction. This is a very simple diagram. I believe everyone has seen this a lot of times. We have standard models, but because of the strong motivation from dark matter and some other a lot of theoretical motivations, we're going to consider some dark sectors, which is almost an independent sector that can only talk to standard model with a mediator. But the problem is how dark matter talk with mediators. Sometimes we talk with maybe the mediator can mix with electric charges, and we regard it as a dark photon. We call it A prime, or it can mix with Higgs, and we call it dark scatter. And the coupling should be proportional to standard model fermion masses. One of the other cases is it can only talk with the standard model neutrino. So The last case is what we're going to talk about today. And in this case, we talk about two general frameworks, which is first, it literally plays role as the mediator. You see, so this is the standard model, and this is the dark sector particles, and this is the dark firm to be the dark matter fermions chi. And so this is an S channel diagram. You consider a vector gauge boson here. On this side is a T-channel diagram. We have a mu with a nu, chi, and phi the same vertex, and the dark matter should be produced in this way. And we mostly consider the cosmology for decoupled neutrino, which means the temperature is mostly below 1 MeV. And dark matter chi is solely produced from interacting with neutrinos, and mostly from nu to chi pair production. And later I will show that of course, there should be various different channels, but mostly this is the most general case, and probably those are not as important as we expected. So again, for the thermal history of dark matter, chi can be produced from neutrinos. If the coupling is large enough, of course, they can enter the thermal equilibrium sometime later. But mostly because the time is late, we don't worry about the BBM bound for N effective. But we do need to worry about the N effective bound from CMB later. I will show a plot for delta N effective at the end of this talk. And if we were considering reduce the coupling or somehow, and the dark matter will never enter the thermal equilibrium, but will in turn behave as the freezing dark matter. And after the dark matter was already produced and the abundance was set up, and the neutrino abundance also set it up, they're no longer talk with each other so frequently, and the rate is lower than the Hubble scale. We could expect about the sin-u-b distortion. And after that, what we are going to talk about. So we have a general framework. We have dark matter produced from neutrinos. We know that, okay, it will go up, and probably if it enters thermal equilibrium, it will go down with the standard thermal mass and until they're freezing out, or just go up and behave as freezing dark matter. So the question is whether two ways, whether two ways are really possible, and how we can compute everything, how we can describe everything in a universal mathematical language, and how they will behave, and what kind of result that we're going to observe today.
Why do dark matter only couple to neutrino?
Well, that's well, I think there are a lot of models, but this is just the one framework that we're going to consider. You can
In what model this is the dominant?
you can think about, for example, maybe it's because of it's in dark sectors there are some heavy neutrinos, heavy neutral leptons. Like if that's heavy neutrinos, it can mix with the standard model neutrinos, and that's the way. It's one of the example I can think about in for
But that's not that's probably the size of the coupling that you're considering is probably too big. They'll probably decay, not dark matter.
Chi but it decay to which? But it decay, it decay to
Decay to our neutrino and
decay to our neutrinos. But from which channel?
Could you show again the two diagrams?
Yeah, because if that's an S channel diagram,
Yeah.
I don't think it can anyway decays, right? If that's a T
Well,
channel,
depends on mass.
I'm just asking in what model this is the.
or you can think about whether there's a charge, like,
Sorry, so which model that you're saying the chi is a right-hand neutrino?
no, I mean,
Chi is some exotic neutrino.
I mean, chi can be some other lattice fermion in the dark sectors, and maybe right-hand neutrino can also be part of the dark sector, and it can mediate, and it can, if chi talks with the heavy right-hand neutrino, and the neutrino will mix with the standard model neutrinos, and find out they can talk with each other.
But the more complicated the thing you make it to be, the less likely this is the dominant channel. Okay, so
Less likely is the dominant.
you're saying this is the main channel for the dark matter production and the annihilation, right? So this is the. I'm just saying, I'm asking an example, okay? So what is an example that this is the dominant interaction, nothing else matters?
We have never considered this problem, to be honest. Well, yeah.
No, but
Mhm.
what you're saying is, I guess, that there is that the phi's interact with a heavier neutrino that mix with low neutrino.
Yeah,
The heavy
that's-
neutrino has a stronger coupling, but decoupled already, so it's heavier.
Yeah, that's what,
And
yeah,
then you
that's
are
what
left
I can
with things
imagine
as
for
effective
now.
interactions.
Yeah, that's what I imagine for now, but that's not, that's without any discussion with my collaborators before.
Okay,
Yeah,
but
yeah, because, yeah.
I can.
Because we indeed see some
I can
people
do that.
discussing this kind of diagrams and we just say, okay, maybe that seems so simple to me, simple and natural to me. And then just go for it.
It's not gauge invariant.
Which one?
The diagram you draw is not completely gauge invariant, right? So it's
Yeah.
naively, there's an electron there too.
No, but not if this is inherited through mix.
But yeah, but with mixings, you need to consider other things, right? So
Yeah.
these things will decay and so on. I don't know.
Yeah.
It's just
Well, if you can, you mean if, because nu is an SU2L, but you want, so you also want to consider electron.
Yeah.
How is that, right?
Yeah.
Yeah, so that's what I,
this will be a higher dimensional operator secretly. You have to.
yeah, so that's what.
You have to
we're-
use Higgs insertions.
Yeah.
Okay, but with Higgs insertions, I'm not sure your story won't change. It's,
Higgs insertions.
Okay, so but we are going to take this effective interaction.
Yeah,
Then we
but-
discuss how to obtain it.
Yeah.
all right.
Okay, the Boltzmann equations. We know these Boltzmann equations, everyone is familiar with that, right? Nu, if there's no mass insertions, we should disregard, talk about in the massless limit.
Something that
But when mass happens, it will be Boltzmann suppressed. So this term will behave as the equilibrium value of chi. And then we have sigma v. And this is the whole Boltzmann equation, homogeneous Boltzmann equation. Remember what is conserved in the scenario is the n chi nu, which is the total number of n chi and times the neutrino numbers. Of course, times the neutrino number of species. So how does this equation behave? And mostly we're talking about the freeze-out behavior, whether sigma v can be included in a universal way, including both relativistic cases or non-relativistic cases, so that we can solve the Boltzmann equation all at one time. So this is what we want to do.
Are the mediator heavy?
It depends on the model. For S channel, we don't want it to be very heavy. Especially we don't want it to be heavier than 2 dark matters, 2 times dark matter mass. So we don't want the production to be like neutrino goes to phi and physical phi, and phi goes to dark matter. That could completely change the story. But for the T channel, it should for sure heavier than chi. Otherwise chi is going to decay. This is the Boltzmann equation. But we're going to talk about the sigma v here, and this is the most natural, the most general definition for the sigma v from the first principle. We can basically compute the sigma v in high temperature limit and low temperature limit, and just according to the famous formula given by Gondolo and Galmini in 1991. So these two cases are easy, but what we were curious about is what's the intermediate cases. So what are the trick?
Where the mediator demo, so did you make some approximation?
Yes, so here we in this case we neglect the mediator mass.
Oh.
Yeah, but no, for the P channel, we take the mediator mass to be same as the dark matter mass. And for the S channel, we take a mediator mass to be 0. And we can parameterize in this way. So physically we can think, okay, at high temperatures, the cross section definitely behaves as a T minus T to the order square on the denominator. And at low temperatures behave as the S wave sigma v. So we do just this kind of very simple trick to see whether they can give me very good behavior. We take 2 benchmarks and we can match lambda in this way, and you see, right? But in general, we need to find a lot of cases like lambda in general should depend on the mass of m phi, and it's also very easy to derive the previous page in the presence of a general mass of m phi, and we can derive the correspondence lambda. It's not very difficult, but numerically, we finally get the similar plot which means you see the sigma V directly numerically computed compared to our trick is almost overlap with each other. So the solid curves are the numerical results. And this kind of dashed curves are what we got from the approximations. So this can help us to do the computation very quickly instead of just dealing with all kinds of numerical issues to perform the numerical integrals of the phase space. And practically, we observe a lot of numerical issues, and that's why we consider to play a trick for this kind of sigma V. So let's focus on the Boltzmann equation once we have this kind of thing. So at high temperature, the sigma V behaves as temperature to the order second. And we talk about this, Boltzmann equation will behave in this way. Because the temperature is high, we're not considering the Boltzmann suppression here. Nu is just Nu squared, right? And we talk about the production of n chi from 0. A quick analytical solution will give us the following result, which is this way. We have this kind of a letter E as the exponential behavior of the production part. And R lambda is a quantity that contains all the interaction information here. We have the sigma V compared with the Hubble scale. So all the thing with lambda means everything like A or temperatures, everything at lambda scale, at the scale lambda. So you can have a look at this. If the R lambda is proportional to the interaction strength. If R lambda is very large, then this epsilon part, this exponential part is going to be large. You can just neglect everything there. So we can simply have the produced n chi goes to this one. It's a stabilized number. So we can say in this case, the dark matter is successfully thermalized. And if not, if the R is much smaller than 1, we should expect, okay, the production is not finished when temperature goes to lambda. But when temperature further to decrease, the production rate, of course, will continue to drop. So we don't expect the thermalization to happen in this case. So roughly, we can expect R lambda equals to 1 to be a critical behavior of whether dark matter is thermalized or not.
What is n chi news? I got lost with the notation. N chi nu is what?
N chi nu is the total number of chi nu.
Oh, but sorry, chi and chi nu are not the same thing. So then, what is chi and chi nu?
Here. Yeah, so chi is the dark matter, nu is the neutrino, and n chi nu is the sum.
The sum
of
of
the
it.
total number. Yeah, low temperature. We're talking about low temperature behavior only if that's thermalized before. Otherwise, we just keep the particle number there. Freeze out. Well, freeze out is something like everyone knows how to solve that. But if we play a trick, we can see that when temperature is very, very, very low, we can neglect the equilibrium value, and the particle just behave as a constant. The y just behave as a constant number. And when temperature is very, very high, relatively high in the freeze-out region, they still kept in equilibrium, and the particle number of chi will behave as the same as the equilibrium number, of course. So the thing is at the middle, right? So this is the Boltzmann equation. So what about in the middle? In the middle, we still play a trick to fix that. Well, this trick simply talks about how the number density behaves in this way. So XFO is the freeze out X. When X is very large, it simply behaves as the flat curve that everyone knows. When it's small, it's basically the equilibrium value. But when it's between that, so this is a number that we just wrote this general form to fix that. And once we match the boundary conditions from this side to that side, and we can solve this kind of coefficients, right? And then we can have a piecewise expression for the y in all time period, and basically behaves in this way. Again, the solid curve is from the complete numerical solution. And those dashed curves are from those approximations. So you can see from the high temperature approximation, we can analytically behave in this way until some temperatures, because, and of course, in that approximation, we never see the curve drop, right? And from some point, we can switch to low temperature approximation. And if you want to be more precise, you can just solve where these two curves can hop with each other, can cross with each other, and regard this point as a boundary condition for different approximations. And L will be able to drop. Question?
So it's for finite medium mass, don't you have to take like the decay, inverse decay with mediator?
Yeah, I'm going to talk about that.
Okay.
Yeah, sure. Freezing or not, this is what I just talked about. This plot is completely numerical. You can see for the red curves, it just goes up, thermalized, and freeze out. For blue curves, goes up, not high enough, it doesn't freeze in dark matter. And you can see the crossing point, one is, our lambda equals to 1 should be between 0.7 and 1.7, right? And these two curves, one is here, it's flat. But this one is slightly higher, just thermalized and immediately freeze out. So our lambda equals 1 is indeed somehow in the middle between that. It's the critical point for the freezing dark matter or freeze out dark matter. So anyway, freezing or not freezing dark matter or freeze out dark matter, it's just a different behavior of the same Boltzmann equation. And there's no way to treat them differently. We can just input the parameters into a general solution framework so that we can scan over all the parameter spaces to see the dark matter abundance, right? So that's the whole point of this picture. So that's the question, one of the most important questions that people will consider here, which is the thing that will happen here. So as I have said, we don't want to consider the decay for dark matter in the S channel that dark matter can go to chi. So we don't consider the dark matter is heavier, the mediator is heavier than the 2 times of dark matter mass. So, but indeed we can have phi physically produced, or it goes back, and then decay back to neutrinos. Or we can have the diagram, the neutrino goes to 2 phi, neutrino goes to 2 chi directly. This is the main diagram. Or chi can directly talk with phi, all these kind of different channels, right? Well, this will indeed contribute to some uncertainties. In some extreme cases, people will going to consider, we want to see that if the dark side coupling is so extreme, then maybe the last channel is going to dominate completely change the picture. Well, one of the single argument for me, especially actually for my collaborators, after several discussions, well, the thing we're going to consider is we can consider some models that will work. We know for some other couplings it may be another story, but we want to consider some of the cases. Especially, we're going to consider those two couplings from the dark side or from the standard model side. Those two couplings are not too different from each other. And in those cases, are where this kind of work are mostly based on. And we want to show that in this kind of framework, we have an interesting cosmological imprints. And actually, we're not aiming to give a framework that can include extremely exhaustingly everything, especially including those cases.
For this S-channel model, for example, it looks quite unlikely to me that the coupling vector with neutrino is similar the coupling with this chi. Basically, for the reason that Dan mentioned, the coupling with the neutrino is secretly higher dimensional operator. So it is conceivable that they are actually of the same order.
Okay. Yeah. So, that's kind of compromise that we actually did in some middle steps in the research, but yeah, those kind of comments is also what I was considering and also discussed with him a few days ago. Yeah, so I think maybe sometime we're going to talk about it later. Maybe some other interesting cases going to happen. Yeah. So let me finish this. Why it doesn't work again? Okay. So in these cases, so one of them is D channel, one of them is S channel. We can see that the dark matter abundance is almost overlap with each other, unless, as we said, in S channel, some interesting thing can happen. Maybe some people expect like the dark side coupling is more natural. It's larger to be more natural, right? Yeah. that will change the story. But if that's not the case, we're claiming that either for T or S, dark matter bound is not to be significantly changed. Yeah. But we can see that for either case, for the same mass of the dark matter, we can have two couplings to have the correct dark matter abundance. And of course, that's one corresponding to the freezing dark matter, one corresponding to the freeze out dark matter. And the large coupling corresponds to the freeze out dark matter. Right. And also, dark matter in this mass range is considered to be warm. And in some cases, people is very unlikely to consider this kind of warm dark matter is going to occupy the whole abundance of dark matter. Maybe we wanted to occupy only like 10, let's say 10% or something similar to that. And in that case, and to consider that cases, we just plot two different curves. One for dark matter one for this kind of dark matter to occupy everything, and one for dark matter to occupy only a part of the dark matter cases. And we're going to see that Lyman-alpha constraint is one of the most important motivation that we're going to consider that. And probably people can expect like warm dark because dark matter is too warm, we don't want it to have too many this kind of stuff in the universe. CNUB distortion. So, okay, what is CNUB? We can talk about a concept. We know everyone is know about kinetic equilibrium, but we need to distinguish the kinetic equilibrium of which particle. Kinetic equilibrium of nu and chi are both kept by the scattering between nu and chi. But the scattering rate is determined by the number density of the other pieces of particles. You can see that if we are talking about a lot of neutrinos and a very few number of dark matter after dark matter is freeze out, or it's just a freezing dark matter, the number of them is much smaller than a neutrino. In that case, the dark matter itself is just there, but for neutrinos, right? There's a lot of neutrinos, but it's very rare for a neutrino to see the dark matter. But the dark matter is very likely to see the neutrino. So in that case, the dark matter is always kept in thermal equilibrium. It's very easy. But for neutrino, it's very likely for the neutrino to left the kinetic equilibrium. So that's the key point. You can see that from tau is basically the time range, how neutrino is out of kinetic equilibrium. And the other one is for chi, right? For chi, right? You see, if neutrino number density is large, then the time is large. Then time range, like the interaction rate is very short. For neutrino, for the neutrino, the interaction time is very large. And if the interaction time is large, then it's very likely that the neutrino doesn't talk with anyone. And the kinetic equilibrium is likely to be broken. So in the initial condition, at the starting point of kinetic equilibrium is going to be left. Then this is still the Boltzmann distribution curve there. That's kept by the kinetic equilibrium. But after that, if some other energy ejection happens here, for example, the dark matter we know dark matter is freeze out, dark matter is there, but that only means the dark matter interaction is really weak, really rare, but not exactly zero. There's very occasional chance that the dark matter still goes to a neutrino. And this kind of neutrino will drop into the high energy tail of the Boltzmann distribution. And because neutrino is already out of kinetic equilibrium, and the energy tail will be there, it won't go back until the redshift will change something. But the story is, for example, the tail is here, and the redshift will change it to the low energy behavior. But after this time period, another high energy injection still happens here. Okay, so gradually this kind of high energy tail rays will be everywhere continuously on the high energy tail, and so that's why we can see something raised in the high energy tail of the CNUB. So if we want to solve it exactly, this is a Boltzmann equation. Again, this is a Boltzmann equation, but for now we cannot use the homogeneous Boltzmann equation. We have to talk about we have to solve for F, not for N, because now we care about the P distribution. F is no longer at the equilibrium form. We want to solve for a delta F, how F is changed from the original one. And the collision term is what I just said, is dark matter goes to nu and it goes back and inject into the high energy tail. So it's still the tradition. So it's still the sigma V that we talked about before. we solve for the case where the kinetic equilibrium for the neutrino is broken. So it's basically tau nu, which is the inverse of the rate for the neutrino interactions to keep the kinetic equilibrium to be larger than the inverse of the Hubble rate. And a quick solution is given by this. The delta F is this. And here are a lot of different parameters. And the important thing is the neutrino flux per energy of the neutrino is proportional to the inverse square of the neutrino energy. But traditional Boltzmann suppression is exponential. So that's why you can see that the energy tail is significantly raised at high energy range. We'll pick a benchmark. We'll pick a point there. So this is we talk about the T-channel diagram that which shows the coupling to be couple coupling to be here. So we want to occupy 10% of dark matter. Coupling is 10 to the order minus 5, and dark matter around K is 0.1 keV scale. So this is the freeze-out dark matter. And a computation shows that the neutrino starts to free stream at x equal to this number, but the freeze-out happens much more before that. So at least for now, we're safe. We're safe. We can just go ahead. The dark matter has indeed already freeze out when neutrino starts to free stream. So this is the C/V distortion we're going to talk about. There is a sharp drop. It's because the dark matter energy is there. It will never contribute some infinitely high energy to the neutrinos. That's why there's a drop there. Below a certain threshold energy, dark matter can do something. So those black curves are some other interesting thing. People are talking about those kind of different sources of C/V distortion. But I mean, of course, we still hope some experiments can really discover that. But the point of this plot is this kind of distortion of the C/V is significantly higher than all the other sources by several order of magnitudes. Well, someone told me that things could be more interesting if we talk about high neutrino tails, because if we can consider general neutrino self-introduction from some other kind of some other thing like DSM-B or some other thing, and that's part of the thing we're going to continue to work on. And effective. That's one of the most important things that we're going to consider, because that's what we really have observed, right? So we argue that there are two sources of contributions to ineffective. Before the neutrino decouples, we just talked about that dark matter is produced mostly after the neutrino decouples, but before neutrino decouples, slight number of dark matter is still produced. So we're talking about neutrino goes to dark matters, but neutrino is in the thermal bath. So the thermal bath will inject some part of the energy goes to neutrinos, and neutrino will contribute that energy to dark matter productions. So the result is the total energy in the new chi sector is increased, right? So this process in general will increase the effective neutrino numbers. Well, after the neutrino decoupling, so this is a separate sectors. The dark matter will be significantly produced after that. Neutrino will contribute a lot of energies into dark matter, while dark matter behaves as matter, not radiations. So in this case, although dark matter will finally give back some cases to neutrinos, in general, because neutrino still overall gives part of the energy to the chi, this will contribute a negative contribution to the ineffective. In general, all this kind of thing can be directly solvable by just solving the Boltzmann equation. We can just tracking the evolution of all the relevant stuffs, like the mediator, neutrinos, and other dark matter particles, and some other standard model particles if necessary, to solve this kind of Boltzmann equation, and we can exactly track the number of the ineffective that can be produced finally. The current constraint, I believe everyone is familiar with that, is we have delta ineffective at 2 sigma levels can be larger than this negative number and smaller than this positive number. And we have some experiments that claim that can observe the delta ineffective to this kind of smaller numbers, right? So the plot for the ineffective, this is the number, as you can see that we can have a significantly negative contribution to delta N effective. For this blue, this kind of shaded region is that dark matter is overproduced. We don't want that. For the other regions, here you can see that we can have too much positive contribution to N effective because the coupling is very large. The dark matter is produced a lot at the early stage. And here we have a lot of negative contributions of N effective. And that's one of the interesting things that we can expect from this scenario. The last one is the Lyman-alpha constraint. So people probably know that this is warm dark matter because warm dark matter is something between hot dark matter and cold dark matter. This dark matter is very light, which means they have a relatively high velocities. Even if, like, we can say, okay, X, well, they still freeze out at a relatively large X, right? But the point is that the temperature is already much closer than traditional WIMPs compared from now. So the redshift won't contribute a lot of things to suppress the velocities. And as you can see, the X for freeze out for one of the benchmark that I talked about before is around 5. So it's not that cold compared to the traditional cold WIMP dark matter. So after we examined those kind of things, we found the dark matter is indeed very warm. Well, the warm dark matter, what can it tell us is that when dark matter really exists in the universe and travels very fast, it will pass through a lot of small structures, which will have some interactions and will be observed. But one of the most important things to quantify this kind of free stream length is the free stream length of the dark matter. Remember, this is the free stream length. This is not like the mean free path. Free stream length means the dark matter, how long can the dark matter travel after once it's produced. So it's actually relatively familiar things in the literatures. So I'm just going to briefly review that. And some of the literature is just do an estimations, but if you want to calculate from first principle, you can just follow Copen-Turner's textbook or something that people will do in the literatures. Is we calculate how long the dark matter travels from the dark matter decoupled temperature. And the velocity behaves basically this way. But the important thing is the scale factor because we move across both the radiation dominated case and matter dominated era. So we should focus on the evolution of A. The dependence on temperature is different in those two different kinds of era. We don't want to consider a specific number of lambda, but what is important is the average of lambda. And the variation depends on different initial condition of P. And we want to talk about the average value of P. And just an approximate behavior of P. But overall, to see the result, we still do the numerical performance. And we show a lot of great agreement between those analytical approximations and numerical solutions. The plot for the Lyman-alpha constraint, the important thing is the gray shaded region is completely ruled out. And that's part of the reason why people don't like to consider warm dark matter to occupy everything in the universe. And you can see if you want this kind of dark matter to be the whole story, then only this part and this part are allowed by the Lyman-alpha experiments. But if we consider dark matter to be only part of the story, things will be much more easier. So that's why that's my understanding. That in at least in this project, this is one of the motivation we're going to consider that. And I believe that's also one of the motivation that people believe that part of warm dark matter is a small part of the story, not the whole part of the story, right? So summary, we talk about how dark matter produced from nu, solely interacting from nu. Both freeze in and freeze out productions are possible. It can be discussed and calculated under the same universal framework. And we can have the parameter spaces for different m chi and different couplings. The cosmological imprints includes the most important thing for me is the CNB distortion, and of course the delta ineffective productions. We can expect both positive and negative delta ineffective contributions that can be observed in the future experiments. And of course, because of the Lyman-alpha experiments, we are going to kill a lot of parameter spaces, but both CNB distortion and delta ineffective are still available after considering that kind of constraint. So I think that's all for today.
So C on B, why do you say that is the most interesting? So then it's difficult to check, right?
Well, the thing is, why is that difficult? I think it should be defined by some experimentalists. Well, if some people keeps encouraging people to do, okay, some neutrino people is going to say that is not that difficult to observe. Trust us, we will do it sometime in the future. Then of course we have one of the motivation to talk about it, and that's historically that's what really happens to us. That's why we put it as the most important thing. And to be honest, I remember I have one discussion with my collaborators because what my initial thought is to put the ineffective to be one of the most important selling point of this work. But he seems to be preferring the CUB distortion. And
No,
especially,
if that, I think if that would be measurable, would be very exciting, of course.
Yeah. Ptolemy claims they can measure for this kind of range. Yeah, not here, but here. That's why I say it's interesting. Well, I hope that experiment can be finished sometime later. But so that's some neutrino people that told me.
Is some kind of.
It might be worth looking into E6, the group E6, which has extra neutral leptons.
E6.
Yeah,
No, he means the group E6 extensions of the standard.
Extension of standard model.
Go from SU5 to SO10 to E6. E6 is the next.
Okay. But you mean some of those kind of big models can contribute, but how can they contribute to some other neutral leptons or?
To produce extra.
Well, there are extra U1s, for instance.
Okay, after U1. Probably as a UV completion of this scenario, right? I'm not familiar with the E6.
It
Okay.
has 27 states. That's fundamental. You have extra engaged bosons and neutral leptons.
Could you go back to the some flaw with couplings and the limits on couplings?
This one.
Okay, so this is assuming the two coupling is the same.
For S channel, we did this. If you vary it by just 1 or 2 order of magnitude, the contour won't deviate a lot. But if like by 5 order of magnitude, the story is likely to be changed. For T channel, I don't think there's any problem.
For T channel, there is only one coupling, that is the Yukawa.
Yeah.
5 T
Yeah.
Yukawa.
Yes.
That's also secretly higher dimensional.
It is.
It is.
Well, what is the size of Yukawa that you need?
Yukawa is just this one.
Oh, it's
It's just this one.
But there's some physics not far away from weak scale. Right, because these are higher dimensional operators. It's supposedly some v square over some scale square. Right, this coupling I should read, at least one of them is on this order.
S4 is T channel division 5, I guess.
T channel, well, depends on the model. Yeah.
Yeah, but maybe at the minimal dimension 5.
At minimum dimension 5.
Yeah. Maybe it's not great for T channel.
Oh, the question is really the thing that you integrate out, right? It's going to change the story. If you summarize that thing,
Yeah.
then it's going to summarize this as well. Summarize the dark matter as well. I mean, there's some reason I think people don't consider like a neutrino is the only source of dark matter. I think it's just difficult to think about a model that this is this is the
Maybe the theoretical motivation from the UV scale is relatively weak. Is that what I mean?
Yeah, I just, you usually, at least you want to make sure there's at least one model that does this, right? So I think the question is that if you integrate out some other states, right, to generate this coupling, that may exist, but the things that you integrate out may also change the history, because they can be thermalized, they can decay to your dark matter. Right, so that it's not possible to write just straight renormalizable models for this.
Mhm.
But does this model impact, for example, stellar cooling, like supernova cooling? So you have a neutrinos that couples to dark matter. And just one the neutron can just dark matter could be emitted from supernova and can change the cooling a little bit.
Should be heavier than what, 50 MeV?
Yeah, but what is the typical mass scale if that's the case?
If the mass is about 100 mega electron volt,
Yeah.
you won't have to worry about that. But
Yeah,
if the
sure.
mass is,
Should be above 50 MeV to
Yeah.
avoid that. If not,
it could be that the coupling is weak enough and it's already fine. But I just wonder if there's a potential constraint from that kind of stellar.
But you mean it can also happen for the sub-MeV case, right?
It's easier to have that than
Also.
minus.
Oh, okay, yeah, that's probably the thing where we that none of us are even know this before.
Stellar cores, I think KeV is the temperature of the. Right,
what do you say?
in the stars, I think KeV is the typical temperature of the cores.
Quite electron volt, but for supernova it can be as high as 10 mega
Yeah.
electron volt.
Not even that range, that is the car.
No, but in general, you want to avoid any astrophysical problem. Then,
Avoid
yes.
and also if possible get
in
significant.
supernova, red giants, all these.
Yeah, but if a neutrino is the only coupling.
Mm.
Neutrino is the only coupling,
Then no.
then maybe it's slightly better, I guess.
But still coupling is radish, and we
Yes.
should have a neutrino inside supernova.
Exactly, that-
And it's one
yeah.
signal.
Supernova, yeah.
But anyway, you never told us what is the additional state.
Well, I roughly know what is supernova constraint, but I just
No,
I don't know what is the specific thing that we're gonna talk about.
I don't think they consider the UV model.
Exactly, so this applies to the UV model, the extra neutral states that you have to.
Yeah.
UV model is out of fashion.
Out of fashion.
Really?
No,
It used to be required. When you write a UV model, people ask you, is this consistent with supersymmetry? Once you say, oh, it's consistent, can this be embedded in dot?
Yeah, like E6.
Yeah, so you usually those are the questions.
Is this consistent with supersymmetry?
I don't think it's considered in any case.
Any more questions? If not, let's thank Isaac again.
Oh, my.